Swayam Prabha. Digital India. Educated India.
Similarly, when I take paths ending in S2, I advance only the winner path. There is no point advancing the loser path because the subtree between below both of them will be identical, and because the initial product, the initial value from which further product will be computed is lower for one of the paths, it can never give rise to a higher probability path. Not possible. Okay, so this is the crux of the Viterbi algorithm, and we make progress with the discussion. I have a path starting from the subtree to start from S1 and S2. So I have taken only one S1 and one S2. Okay, other S1 and S2 ending paths are useless. So from here now I make observation that there is A1 symbol on the sequence. So from this S1 I get S1 and S2. From S2 I again get S1 and S2. Now I again have 4 leaves, 2 of them ending in S1, 2 of them ending in S2. So out of those ending in S1, I choose the higher probability node. So here this S1 with probability value of 0.012 is more than this S1 with probability of 0.009. Remember, 0.009 is the accumulated probability, okay? The probability of the partial path seen so far. Similarly, 0.012 is the accumulated probability of the partial path seen so far. Similarly, for S2, I get the winner S2 from S1. I get winner S1 from S2. Okay, I advance S2 and advance S1. The observation symbol now is A2. Okay, and then I have finished the observation sequence. The algorithm should now terminate. So from S2 I can come to S1 and S2. From S1 I can come to S1 and S2 again. And at this point, since all the observations are over, I simply compute the total probability at each of these leaves, and I find that the winner probability is 0.0081. So the path that I have discovered for A1, A2, A1, A2 now can be traced by tracing the back pointer from the winner leaf. Winner leaf. So the path for me would be S1, S1, okay, S1, S1, and then S2, then S1, okay, S1, S1, S2, S1, and the accumulated probability is 0.0081. Okay, so this Viterbi algorithm is the technique which is used for decoding. The term decoding means find out the best possible state sequence. Now, where is the complexity reduction happening? It is not very difficult for you to see. What is the trick? The trick that is happening is that at every level I kill off, okay, nodes which are going to be useless in future. So if there are t states, okay, if there are t states, then at any level I retain only t states for advancement. Okay, at any level I retain only t states for advancement. So at the first level I have start. In the next level I'll have t nodes. In the next level also I'll have t nodes. In the next to next level again t nodes. In the next to next level again t nodes. Never am I encountering a situation where at a particular level I have to deal more than t nodes. Okay, so that is why the number of paths amongst which you have to search is t into L rather than t to the power L. which is a drastic reduction of complexity. Okay, and this is happening because at every level I am able to eliminate a huge number of nodes and retain only number of nodes equal to number of states. Therefore, if there are L levels corresponding to sentence length of L, and at each level you have T states, then you have T into L complexity for the algorithm. Okay, so we have presented one of the cardinal ideas of machine learning, the whole of AI, I would say, and this algorithm has been applied in signal processing, speech processing, economics, okay, urban planning, social sciences, a very, very important pillar of artificial intelligence. Okay, so at this point of time, I would like to take questions, comments, because we have finished discussing a very important topic, namely bit-error decoding. So let me,
Sir,
yes. So let me just
sir,
stop.
There should be T complexity, right? Means why T into L?
T into L because at every level you have T states, okay, T nodes to expand, and there are L levels.
Okay, I mean the number of paths are T, right?
The number of paths are T. Okay, yeah, number of paths are T. Yes, that's right. Number of paths are T. No, but the complexity of the algorithm, okay, the amount of search you have to do. So the complexity of the algorithm is in the number of operations you have to do. So that is T into L, or that is order L. T is constant. It increases with the
Yes.
with the length of the sentence instead of exponential on the length of the sentence. Okay, so I can stop sharing and now take questions.
The very first thing is Anubhav wants to ask is that he wants you to address the doubt regarding the tag set in the Brown corpus regarding the assignment. So
Okay.
the default.
Just a minute, Riptesh. I'll come to that. But I want to know on Viterbi if there are any questions, comments on Viterbi.
Okay. The next question is it right that there are tags and states and words which are hidden? If so, what about the reverse scenario being implemented, taking words as states and tags as observations?
Okay. So whose question is this?
Jalai Dhaval Shah.
Okay. So the question is, why not directly deal with PS given O? Okay. So one of the reasons, of course, you will deal directly with PS given O in other algorithms like maximum entropy Markov model, conditional random field. Okay. There you don't have to apply Bayes theorem and have to deal with two probabilities, the prior probability and likelihood probability. The reason we are doing so is because of the machine. We are constrained by the machine that we are using. The machine is hidden Markov model, and that gives me transition probability and observation probability. Okay, so I cannot directly deal with PS given O. I have to convert it into the transition sequence probability and the observation sequence probability given the state sequence. Okay, so the machine is limiting me to do the computation this way, okay, by turning the probability around. But in discriminative models, where we deal with this exact expression PS given O, you will see that that is the case. Okay, we deal with parameters of PSI given OI. Okay.
Sir, the next question by Saurav is, further subtrees will be identical due to Markov assumption, right?
Yes, that's right. It is due to Markov assumption. The state probability depends only on the previous state due to Markov assumption.
Mohit asks, in the slide developing the tree, I have a doubt. There are two arrows from each state, but the probabilities don't add up to 1. Why is that so? I might have missed some point.
Okay, so see here, R, G and B, 0.3, 0.5, 0.2 adds up to 1. U1 goes to U2 and U3 or remains in U1, probability adds up to 1. Okay, 0.1 plus 0.4 plus 0.5 adds up to 1. Now when I take the product, I get 0.03, 0.05, 0.02. Okay, so U comes back to U1 on RGB with this probability 0.03, 0.05, 0.02. U1 goes to U2 on RGB 0.06, 0.24, 0.30. Okay, U1 goes to U3 on RGB 0.15, 0.25, 0.10. Now, if I take a single observation, okay, let's say R, and single state, starting state U1. So on R, U1 coming back to U1, going to U2, going to U3, on R, should that add up to 1? So 0.03, 0.06, 0.15, that doesn't add up to 1. And it should not add up to 1 also. Okay, so if I'm taking only the transition probability and sum it up on the row, it should add up to 1. If I take only observation probability, sum it up on the row, it should add up to 1. But the joint probability of going from a state to another state on a particular observation, that need not add up to 1. Just think about it and convince yourself. Okay, this is joint probability. Okay, next.
Right, sir. So Akshay asks, why are we considering two states S1 and S2 for further subtree computation instead of just moving further with S1 as it has the maximum probability?
Oh, that I do not know a priori. Okay, I have to keep both possibilities alive, S1 and S2. So if we're suggesting some kind of depth first computation, advance S1 completely, that is one method of doing, but depth first, breadth first computation are not as efficient as the Viterbi algorithm as shown. Okay, so your question that explore a path fully, that will lead to a lot of useless computation, because below S1 nothing. If we go from S1 to this S1, the leftmost S1, then none of the paths under S1 will ultimately be winner.
The next question is, Karan asks, suppose all paths have the same probability, say 1 by t, then how is Viterbi algorithm implemented?
All paths have this. Oh, if you mean if there is a tie, is it that two partial paths are ending with the same probability? Is that the question, Karan?
Yes.
Yeah. So if both S1s had the same probability, then how will the Viterbi algorithm work? Then you have no choice. Okay, you will have to advance both the paths and kill off the subtree at a later stage.
Okay. Jalai asks, is this algorithm optimal?
Optimal in what sense, Jalai? What do you mean? Oh, does it give the best possible path? Yeah, it gives the best. It gives the best possible path. Yes, it is optimal.
Kartavya asks, how do we handle the problem of vanishing probability?
Yes, good question. So we are taking the product of probabilities, and the product keeps on multiplying, and for a very long sequence, for a very long sentence, the probability will be almost 0, and then you will have problem with precision in your computer. So you can deal with log values, okay, and work with the sum, that doesn't fully eliminate the problem. Well, the problem remains. Okay, what else can I say? The problem remains.
Okay. Vipul asks the time complexity should t square into L. At each level, will we be considering t states from each of the t states?
Yes, right. You're right. The complexity is t square L, because you are at any level from amongst the states, you are finding out best possible S1, best possible S2. Okay, so you are finding max for each of these states. So for each state, you are carrying out a linear complexity algorithm, linear in the number of states. So for each of the states, complexity is t. So for t states, t square.
Right. So next, Vineet and Karan have opined that it should be t square into L, but I think Abhishek says that I think we are discarding t states and are considering another t state, so the complexity might be t into L. But that I think this is just a discussion. Vineet asks.
No, but one sec. So remember that you are doing a max find. Okay, you are finding the maximum value, and finding max is linear time. So you are doing a linear time search for each of the states amongst t possibilities. So that's why t square.
Vineet asks, how is problem of ellipsis dealt with in POS? As in, some words may be unspoken, but the grammar would require us to go through certain tags.
Problem of ellipsis is not dealt with in POS. Okay, there is a reason why you deal with an NLP pipeline, or you conceive of natural language processing as an NLP stack. Okay, and it goes to a very important management principle. This is called separation of concern. Okay, so ellipsis is at a very high level of NLP, namely at discourse. At the part of speech tag level, we assume the whole whole information is in front of us. We do not worry about meaning. We do not worry about parsing, co-reference, nothing. We just worry about sequence leveling with respect to grammatical categories. So ellipsis is not dealt with in part of speech tagging. In fact, part of speech tagging very blissfully thinks that ellipsis doesn't exist.
Right. So just one second. Yeah, and Muhammad Ali Rehan asks, if we are at a given state, then we choose the highest probability. What if this causes us to reach a state from where all outgoing edges have low probability?
Okay, the Viterbi algorithm insists that at any level, look at all the partial paths, and amongst all those states ending in, let's say, S1, choose the one which has the maximum value. So can you repeat the question now, Diptesh?
Right. So the question was, if we are at a given state, then we choose the highest probability. What if this causes us to reach a state from where all outgoing edges have low probability?
Yeah, so this is the vanishing probability problem, which one of the previous questions asked. So if it is low probability, then you will have this precision problem in the machine. And I think so. You are asking an implementation question. What do I do in case of this kind of low or vanishing probabilities? So really, you cannot do much. If you are dealing with long sentences, you most probably have to work with the log values.
Right. So the next question by Shreya is, how do we deal with previously unseen words / observations in this, as in out of vocab words?
Okay, that's a good question. You will encounter this in part of speech tagging. So unseen words or unseen entities is a uniform problem across whole of machine learning. Okay, what if you encounter a new entity in test situation that was not seen in the train situation. So coming to part of speech tag, you encounter a situation where the word a word appears in the test sentence which never appeared in the training data. Okay, training data. So this is the class, what is called the classic data sparsity problem, and you will have to apply some kind of smoothing. Okay, you will have to apply some kind of smoothing, and here I refer to you to the excellent chapter on smoothing in the book Statistical Natural Language Processing by Manning and Schutz. Okay, TA team, can you please write it down? It is there in our reference list also, which is there on the course website. So go to the chapter on smoothing. So you have things like add one smoothing. Okay, then there are quite a few techniques. Add one smoothing is one of them. There are quite a few well-known techniques which are used for smoothing. Now, what is the intuitive idea is the following. Suppose you have seen in the training corpus or in the testing sentence, you are encountering a word, let's say procrastination. Okay, so procrastination is a new word which never appeared in the training data. So many techniques are applied there. Some people make use of morphological information. The word ends in shun, T-I-O-N, so it must be a noun. Okay, so so you give the default tag of noun for this. Sometimes what you do is that you see the preceding state. So in most of the preceding states, you had a, so suppose the preceding state was noun, okay, and in most of the cases a noun was followed by a verb. Okay, so then what is the question? The question is, I have seen a noun, now the word is procrastination. What tag should I give? Procrastination was never seen in the training data, so I do not have the observation probability there. But noun was mostly followed by verb, so I'll give the tag verb to procrastination, which will be wrong. Okay, which will be wrong. But this is based on the previous observation. So these are the heuristics which people apply. But you know, a more thorough discussion would be smoothing. You can read up smoothing, but I would like to cover smoothing at some point of time in the class.
Okay, so yesterday Vatsal was asking why was the HMM related to the earn example is of order 2.
Oh, why is it of order 2? That means the
Bigrams.
bigram. So why do we assume that the probability of going to the next arm depends only on the current arm? Maybe that is the question. Okay, so well, this is the Markov assumption. The next arm I pick up will depend on the current arm. Okay, the previous arm which I visited is not making an influence. Okay, that is an assumption. So the question of the answering the question why is not easy here because it is an assumption. Okay, it's the bigram assumption.
Right. So yesterday also someone had asked how to deal with an unseen word in the test set, which you have just answered. But Kaveri had asked yesterday, in observation probability table, column sum should be 1 because, for example, red ball should get selected from either of the earn 1 or earn 2 or earn 3. Is this understanding correct?
No, because the sum of probability being 1 applies to the conditioned variable, not on the conditioning variable. Okay, so probability of B, C, D given A. If B, C, and D exhaustively enumerate all the states, that should be equal to 1. But probability of A given B, C, D, where B, C, D are exhaustive states, on the conditioning part, they remaining on the conditioning part doesn't add up the probability to 1. So doing some algebra will convince you that. Okay, so the variables exhausting the sample space coming from the conditioning part doesn't make the probability add to 1. Pooja, can you explain what the question was?
So in the definition of HMM, we have taken different notations like S, V, A, B, and pi. So today I got it. It was the initial probability you told.
Yes. Yeah.
Yeah.
S, V, A, B, pi. Yes.
And the next question is, when all the joint probabilities are equal, that will lead to exponential complexity, right? This is by Saurabh.
When all the joint probabilities are equal, oh yeah, if all the partial path probabilities are equal, then that will lead to exponential complexity because you cannot kill off any of the paths. That's true, but that is extremely unlikely.
So,
Yeah.
for this point, I wanted to ask, this won't be necessary, right? Means, we won't, we know that at each level, if there are two paths which are giving same probability and we can't kill, so but we will still go with one because we know after these they will have the same probability, right?
Achha. So yeah,
So,
okay. Yeah. So amongst all the paths ending in the same state, if all the paths have equal probability, then choosing any of them is fine.
yeah, but just we have to we will have space complexity because we would have to note down the other paths above annotations, right?
Yeah, other paths which are other paths towards the root, right?
Right. Yes.
Yeah.
Yes, sir.
Yeah, okay, but you have a good point there. Yes. So if equal probability, then you can choose any of them and you are fine. Okay. And if unequal probability, then also you choose one of them, you are fine. But I think the time is up now. Okay, we'll take the remaining questions in the next class.